Thank you very much, Anton. Thank you for the invitation and also organizing these colloquium series. I attended, I would say, quite a few and learned quite a lot, and particularly in the early days of the pandemic, this was really fantastic because our on-site colloquium was not taking place, and this was kind of the exposure that we all needed. So before I start, I'd like to thank my co-workers. I underlined the names of people, postdocs and students who have done most of the work, experimental and theory. And as Anton said, I'm going to tell you about recent experiments. But before I do that, I would like to motivate, and somehow I'm having difficulty in, yeah. So I stepped a bit, yeah. So basically I'm going to tell you about strong correlations in atomically thin materials or two-dimensional materials. And just as a reminder, I would like to sort of advertise this really fascinating field where sort of materials with very different functionality or properties can be put together into a so-called van der Waals heterostructure. And the nice aspect of this is that unlike the usual materials, again, materials with very different properties like semiconductors and semi-metal superconductors can be brought in direct contact with each other. And this results in novel electronic and photonic properties of the combined heterostructure. Now, one aspect of these materials is that they generically have, the heterostructures generically have reduced dielectric spinning, at least as compared to semiconductors, the traditional semiconductors. They allow for controlling the charge density via gates. And typically, at least for the semiconducting materials that I'm going to talk about, the carrier mass is relatively heavy, on the order of the free electron mass. And this all implies that one can have strong interactions and tunable strong interactions in the system. Now, there is an additional, a really amazing degree of freedom in this material. That is, when one stacks these materials to form this van der Waals heterostructure, one can also introduce the twist angle. And this results in the appearance of a superlattice, a moire superlattice, which can exhibit flat bands. And in that case, the interactions become the dominant energy scale, and one can explore interesting, strongly correlated phenomena. Now, I'd like to summarize or sort of convey my picture of this, that I would like to say that what we're dealing with here is a new research field that is bridging the more traditional quantum materials and the cold atom quantum simulator. So we have a much higher degree of control and in situ tunability as compared to quantum materials such cuprates. And unlike the cold atom systems, when one creates a synthetic material, there is real functionality. You don't simulate superconductivity, you observe and measure superconductivity. And I guess it goes without saying that the most spectacular result in this field is obtained in magic angle twisted bilayer graphene. And this goes back to 2018, the results of Pablo Jarillo Herrero, which was followed up by a large number of groups with outstanding results demonstrating in one material intertwined superconducting phases, correlated insulator phases, as well as quantum anomalous Hall effect, and so on. So what is really amazing is that using a gate, one can change the electron density in the same material and explore different quantum states in one material. Now, what is really playing a crucial role in magic angle twisted bilayer graphene is the existing of moire superlattice, which ensures that out of Dirac fermions, one obtains flat bands with their very small bandwidth, small compared to the characteristic energy, interaction energy scales. Now, this begs the question whether an external superlattice potential is really necessary to observe strong correlations. And to judge that, let's recall that what is really important in determining whether correlation effects that arise from interactions is important is the comparison between the characteristic energy scale of kinetic energy and the characteristic interaction energy scale. Okay, so basically the kinetic energies characteristic scale is the Fermi energy. This scales in 2D with the density, and then the Coulomb interaction scale as 1 over the distance, and therefore they scale or increase with the square root of the electron density. Now, a way to sort of judge the potential importance of correlations is to look at the so-called RS parameter, which is the ratio of the two. And for Coulomb interactions, this parameter scales with the effective mass, so heavier effective mass is good. Inversely with the dielectric constant, so reduced screening is good. These all make sense. And then it scales inversely with the square root of the electron density. So lower density is good for strong correlations, provided, of course, that disorder doesn't destroy the game. Okay, so if we start out with the small RS parameter, then the electrons will form a Fermi liquid that describes many most metals as well as doped semiconductors. But if we can lower the RS parameter without introducing disorder, then we can eventually go to a state which was predicted a long time ago by Eugene Wigner, which is that the electrons crystallize in a triangular lattice. Okay, so this has been quantum Monte Carlo calculations show that to get there, one needs RS parameters actually in excess of 35. And what happens in between is actually, as far as I know, still not known. At least I definitely don't know, have a good description of how this transition between the quantum liquid state and the Wigner crystal state takes place. So naturally, this is a very interesting sort of prediction by Wigner that has fascinated physicists, and there has been intense efforts to be able to observe Wigner crystals over the last 30 years, and the material of choice in this regard is gallium arsenide, and the principal reason for it is not because of its high RS values. On the contrary, RS is small in gallium arsenide. It's about 1 for electron densities of 10 to the 11, but the quality is very high. So this is the highest mobility system that we have at the moment, where the mobility can exceed 30 million. So, but since RS is larger than 1, is on the order of 1, without, so there is, at zero field, there is no way of seeing a Wigner crystal. So what the community did is to apply large magnetic fields to quench kinetic energy, and then look at low filling factors of the lowest lambda level. And so in this case, the theory predicted that the system would undergo a Wigner crystal state for filling factors less than about 1/5. And indeed, transport measurements, in this case longitudinal resistance, show that beyond the 1/5 state, that the resistance remained very high, and this is consistent with the explanations. Now, a more convincing evidence was experimental evidence, was the verification of a prediction that the Wigner crystal that is pinned by the weak disorder can be unpinned, and resulting in a substantial increase in conductivity if one hits the system with a C drive with characteristic frequencies on the order of gigahertz. And indeed, that here is a result from 2006, which showed that at low temperatures, the conductivity can indeed increase. Now, what I would like to emphasize here is that these are all indirect measurements in the sense that they're consistent with the presence or emergence of charge order, but they do not tell us directly of the existence of charge order. So, so now the new material in game are these two-dimensional semiconductors. I briefly mentioned them. So what is characteristic here is that the effective mass can be large, dielectric spinning is reduced, and when we put these together, we find that the RS parameter can actually exceed 40 for similar densities. So then the natural question is, if a Wigner crystal forms and say at zero magnetic field, then how do we verify, how do we detect the existence of the Wigner crystal? And in particular, can we obtain a direct evidence, say using optical spectroscopy for the periodic charge distribution? And if you look at the numbers, that the lattice constant 20 nanometers, optical wavelengths around 800 nanometers, doesn't look very promising, but this I will try to convince you that by using excitons, this is indeed possible. So here's the outline of my talk. So I will tell you about excitons, or in general, elementary optical excitations in two-dimensional semiconductors, transition metal dichalcogenides. Then I'll tell you about our results on monolayer Wigner crystal, observation of charge order. And if time permits, I will tell you a more recent result, which is the observation of a Feshbach resonance in exciton electron scattering. So very briefly, so transition metal dichalcogenides are actually not all semiconductors. They form a sizable subgroup of more than 5,000 layered materials that we know. So the ones that are of interest for this talk are the semiconducting ones, and particularly molybdenum diselenide is what we use in practically all of our experiments. So basically what I refer to as a monolayer TMD is actually a tri-layer structure where a triangular lattice of molybdenum atoms is sandwiched in between two selenium lattices. So if you look at it from a distance, what we see is that we have an effective honeycomb lattice where A site is occupied with molybdenum atoms and B site is occupied by two selenium atoms. So this is then has similarity with graphene, but the sublattice symmetry is strongly broken, and this results in a large band gap in the high symmetry points K and K prime of the Brillouin zone. Okay, so for monolayer TMDs, this band gap is direct. So this is fantastic. So so basically, therefore, when we look at the optical properties, optical excitations, then we have basically this additional degree of freedom, which is the Valley degree of freedom or Valley pseudospin. Now, in most TMDs, though, since spin orbit is relatively strong, the spin is locked to the Valley. And in that sense, we still deal with excitations with 2 degrees of freedom unless we increase the electron density and basically start occupying the higher energy state. So this splitting in conduction band is about 30 milli-electron volts. In valence band, it's about 200 milli-electron volts for molybdenum diselenide. So let's focus on only one valley. So say the K valley. So what is important, what I forgot to mention, is that the optical selection rules that govern the excitation of an electron from valence to conduction band is very much tied to the valley. So basically, the sense of electronic circulation, the so-called intercellular currents in the 2 valleys, actually determine whether one needs a sigma plus polarized light or sigma minus polarized light for excitation. So so basically, if you go back to the K valley, let's say the excitations are by sigma minus light. So normally we would consider, if we discard interactions, and electron hole pairs that can be generated by exciting an electron from valence to conduction band. But as I've been arguing, the system has strong interactions, and indeed the electron is strongly bound to the hole that it leaves behind, or it can be strongly bound, and lower its energy dramatically to form a bound state, which we refer to as an exciton. Now, one is the stronger the exciton, the stronger the binding of the electron and hole is, then the larger the oscillator strength of this object is. Because remember that when exciton annihilates, it generates a photon, and if the electron and hole are strongly localized, then it is much more likely for them to find each other, so to speak, and recombine or be generated. And indeed, that in 2D semiconductors, the absorption spectrum is dominated by excitons. And one other important point that I would like to make is that if we assume an ideal disorder-free system, the excitons that are generated in the system have translational symmetry, and therefore momentum would be a good quantum number. And when an exciton decays to generate a photon, it generates a photon with the same in-plane momentum due to momentum conservation, which in turn means that only low momentum excitons can decay. So to highlight this better, I would like to go from the single particle dispersion to a dispersion of excitons. Okay, so in this case, what I'm plotting is the energy dispersion of different kinds of excitons that we can generate. What is most important for us is the 1s exciton. And the point that I would like to make is that the mass of the exciton is even larger than the free electron mass, because it's the sum of the electron and hole masses. And it has therefore relatively, let's say, flat dispersion. But most of these excitons cannot decay, even though their energy is very comparable to the k equals 0 exciton. And only those with the smallest momentum that lie within the light cone are allowed to decay. And this will become important later on. Okay, so I also just numbers. So this 1s, 2s assignment follows the Coulomb potential, but we also know that Coulomb potential actually does not describe the electron-hole interaction accurately. One should really resort to a Keldysh potential because of the strong in-plane screening. And some numbers that the binding energy, if molybdenum diselenite is embedded in boron nitride, binding energy is 230 millielectron volts, and the Bohr radius is about 1.1 nanometer. So if you're familiar with excitons, this is still a 1E exciton, but not so far off from a Frankel exciton, which is typical in molecular systems. Okay, so I see that Anton raised.
Sorry, I have a quick question.
Yes.
Isn't it right that one can imagine intra and inter-valley excitons, and their frequencies would be quite comparable, but their lifetimes not? Is that the right thing to think about?
Absolutely correct. And so indeed that you can consider not only the bright excitons that are necessarily intra-valley excitons that can be generated, but if one does a photoluminescence study, that is, apply a high energy laser and let the carriers relax, then one could end up in, let's say, inter-valley excitons where electron and hole live in different valleys. And these, as you say, have comparable binding energies. Actually, inter-valley excitons have lower energy because of the fact that they do not have electron-hole exchange interaction. So bright excitons do have what we describe as the short-range electron-hole interaction. So basically, the way to think about it is that there is mixing between the conduction and valence bands, and to the extent that we're dealing with excitations with the same spin, then there will be an exchange correction. Very small, on the order of 20 times smaller than the binding energy, but in this case, is still on the order of 15 milli-electron volts or so. So the inter-valley excitons do not have that, and therefore even have lower energy. And in some compounds like tungsten diselenide, they play a prominent role in determining emission through phonon-assisted processes. So in principle, even though an inter-valley exciton cannot decay directly, they can emit a zone edge phonon and then decay, particularly in that case, the spin between the lowest conduction band and the highest valence band is the same. That's for tungsten diselenide. For moly diselenide, they do not play a significant role. At least they might be influencing the photoluminescence efficiency, but at least in the absorption measurements that I will show you, they do not play a role. Was that?
Yeah, thanks.
Okay. Okay, so I was going to talk about the photoluminescence measurements, not going into efficiency, but so in these measurements, what you do is you take a high energy laser, generate 3 electron hole pairs, they relax, and basically because the exciton state has lower energy by 200 milli-electron volts, the emission takes place after the electron hole pairs relax by phonon emission to form an exciton. This is also standard in 3-5 semiconductors, that the intraband relaxation is generically faster than interband. Now, what is also possible, though, if we have electrons in the system, the exciton can bind to one of these electrons and form a bound state, which is the counterpart of the H- ion. So if you have seen this in atomic physics, this is a rather peculiar ion where the hydrogen atom has one bound state, a single bound state for capturing an electron, provided the electrons form a singlet. Okay, so in photoluminescence, this binding energy is about 25 milli-electron volts, even though tryon has very weak oscillator strength, and I'll tell you why. They can appear prominently because of the fact that they have lower energy than the exciton. So this, I would say, would be a typical photoluminescence spectrum in a material that is not charge controlled, that has some weak trapped electrons. So you'll see a sharp exciton peak and in the peak from tryon emission. Okay, so now I would like to tell you about charge tunable van der Waals heterostructures, because this is, after all, what we need for the Wigner crystals. So in this case, we embed our monolayer in between, generally between top and back gates, which are graphene layers. And so through the applied voltages and the direct contact to the semiconducting layer, we can tune the electron density or the hole density in this system. And this is a micrograph of let's say, it's relatively simple device with the single monolayer and 2 contacts. So, so if you have 2 contacts to the TMD, you can actually also try to drive a source drain current after while controlling the electron density through the gates. And what you see is that indeed there is a certain gate voltage range where the current is vanishingly small, and then you can inject electrons and increase the conductivity or inject holes and achieve the same way. Now you can do optical measurements on the same device, and you see that when the system is neutral, this is reflection or absorption measurements, you can think of it that way. There's a prominent exciton line, and even before the current turns on, it starts blue shifting, and then there is a new resonance that appears on the low energy side that picks up sizable oscillator strength. Okay, so actually it becomes stronger than the main exciton peak for densities of few times 10 to the 12. So these peaks, or the spectra in general, we can understand them as essentially Fermi polarons or exciton polarons, and I'll try to describe to you sort of how we can think of these in the simplest way. So basically, excitons and electrons are interacting particles. So I will regard excitons as rigid particles that the presence of electrons do not really change the exciton confinement and the size of the exciton. This is an assumption, and it's a reasonably good assumption for densities up to 10 to the 12. So the electron and exciton interact because exciton is a polarizable object, electron is charged, so the resulting interaction is attractive and goes as 1 over r to the 4. So it's a relatively short-range interaction, and it's a density-density interaction. So we can write it essentially as the exciton density times the electron density. Now, because it's short-range, we can actually express the interaction as a effective contact interaction. And this contact interaction strength will be described or would be given by the molecular binding energy associated with the interaction potential. And of course, we need to regularize it by introducing a cutoff. Now, if we really have only one electron and one exciton, then we can actually, this Hamiltonian, we can diagonalize using a variational approach. And we will find that there's a single bound state, and this is the trion state. And the creation operator for a trion, one can write in terms of the product of exciton and electron operators with the wave function that is relatively tightly bound. So basically, the size of the trion is about 2 nanometers, so not so different than that of the exciton. Now, what that means for optical studies is this, that if you look at this expression for the trion operator, and if you recall what I mentioned, that the exciton, when it decays and is converted into a photon, momentum conservation requires that its momentum has to be less than the photon momentum, or that means that only a very small fraction of let's say, the excitons in this expansion are allowed to decay. So what that means is that a very tightly bound trion has a very weak oscillator strength, because this wave function, the amplitude for q equals 0 state, is going to be correspondingly small. Okay, so in return, of course, unlike excitons, finite momentum trions can also decay because of the fact that they also have finite probability amplitude for having 0 momentum excitons. Okay, so now in more general, if you have many electrons, a degenerate electron system, then we can only find approximate eigenstates of this Hamiltonian. And one popular approach, which we borrow from the cold atom work, is to truncate the Hilbert space and allow only for one electron hole pair. That is, the exciton, the mobile exciton, can generate only one electron hole pair in the system. So, this approach works quite well in terms of making quantitative predictions for the experimental observations. What I would like to emphasize here is that, again, once we sort of approximately solve the Hamiltonian, we find that the eigenstates with large spectral weight are the attractive and repulsive polarons. And these are these two branches that we see when we dope the system with electrons. Okay, so the exciton, as the system is doped with electrons, becomes repulsive polaron, and then there is a new branch that is the attractive polaron, which actually, in the limit of vanishing density, becomes essentially the trion. Okay, so now, so for the purposes of this talk, what is really important is this sensitivity of the exciton energy or the polaron energy on the electron density. Okay, and there is more to it. I mean, looking at this, you can say that, well, okay, so it looks like if we have a good theory, we can determine the electron density by looking at the energy of the repulsive polaron. We can do more. And as an example of that, I would like to share with you this data. These are exciton polarons at relatively high fields. and where the electrons form integer quantum Hall states. And what we find is that if you look at, I don't know why my mouse is jittery, but the repulsive polaron in one polarization and attractive polaron in the other, you see that every time the electrons are in a integer quantum Hall state, then there is a cusp in the exciton energy, and this is also associated with line narrowing. Now, we of course check these with the capacitive model. We actually have another way of determining the density, and we find that this agrees very well with what we would have expected, what we expect from the capacitive model. So we can really turn it around and say that, you know, these should be called the Haas-like oscillations in optical conductivity is a way to determine the electron density in the system. Okay, what I want to emphasize here is not so much the importance of determining the electron density, but really that the electronic state matters, that it has its signatures in the polaron spectrum. Okay, so now let me go back to zero field, and then let's discuss how electronic state generically can modify exciton polaron dispersion. So now I'm drawing the exciton dispersion with this additional sort of twist, which is the fact that electron-hole exchange interactions also result for high momenta transverse and longitudinal excitons. These are outside the light cone, so it will so maybe I will not dwell too much into it unless somebody is interested. But basically, we observe what happens at the bottom of this dispersion relation. And this is the undoped system. If you put in electrons, so what we have seen is that there is a blue shift, the polaron, due to the polaron formation, repulsive polaron formation, the exciton energy is blue shifted. Okay, so this is what we expect if we have a liquid state. Now, if the electrons were to form a Wigner crystal state, or are in a lattice, say, due to the presence of an external lattice, then things are very different because the excitons interact with electrons. And if the electrons form a lattice, then the excitons, will see a periodic lattice potential. And they will scatter off these electrons, Bragg scatter, and this Bragg or umklapp Bragg scattering results in the formation of new resonances and the reduced Brillouin zone at the zero superlattice crystal potential, or superlattice potential, I should say. And these resonances, these umklapp resonances, hybridize with the k equals 0 and pick up an oscillator strength. And therefore, they will become visible in resonant absorption, even though they originate from high momentum excitons with the momentum that corresponds to a wavelength that is equal to the lattice moment, the lattice constant, which, as I said, is on the order of 20 nanometers. Okay, so this is the essence of our measurements that I will show you, that basically to be able to see the lattice, we need a de Broglie wavelength of the excitation that is commensurate with the underlying lattice that we would like to detect. With photons, this would require X-rays, and then the sensitivity would be extremely low, and I don't think anyone has managed to see this. With optics, with optical photons, then the wavelength is very large, but by converting photons into excitons, which are massive and can have very short de Broglie, very high de Broglie, sorry, let me stick to wavelength, very short de Broglie wavelengths, we can basically optically detect the existence of the lattice. Now, this is a very simple 1D sort of like model. In general, of course, we have a 2D problem, and we can calculate the excitonic band structure in the reduced Brillouin zone by making a simple assumption where we treat the electrons as presenting a spatially varying R3 potential on the excitons. And you can see that among there are a total of 12 excitonic bands, and 6 are high in energy, and then the lower 6 ones, 2 of them are optically active. I don't know why my pointer, it just froze, but it did. Okay, so hopefully I'll manage. Okay, now it's better. So the laser pointer was not so secret again. Anyway, so the point is that only in this yellow shaded area can we have optically active excitons. Okay, so now to the experiments. Let me finish this, and maybe then I'll take a look at the chat. So this is another sample showing electron doping, attractive and repulsive polarons. And what you can see at a first glance is that not much is happening at these low densities. Okay, but if we look at it more carefully, and we do so by differentiating the reflectivity with respect to the gate voltage, such that we are more sensitive to the changes in the electron density, then we see that in addition to the exciton line, we have a new resonance, which is this umklapp resonance that I was trying to explain. Okay, so it's much weaker than the exciton resonance. But what is important is that its energy splitting at any given electron density scales with the electron density. And the proportionality constant is precisely what we expect based on the exciton mass, and the rest is just the factors that arise from the triangular lattice. So the fact that we have this very nice linear dependence on the of the splitting of the umklapp from the main exciton line is our first strong indication that this peak is not some spurious peak, but really or could be linked to the formation of a Wigner crystal. So to get further, maybe I should stop here. Yes.
Oh yes. I also see a question in chat from Emre, who is asking, how do you make sure that the new resonance is not a magnetically brightened dark exciton?
Okay, so so I don't know if there is. I mean, what exactly you mean by this? I think that's magnetic brightening of excitons at TMD at low fields is not really there. You know, I'd like to hear maybe what you mean by this, but basically these are very strongly bound excitons, and to talk about magnetic brightening, I don't know. I mean, we certainly haven't seen this experimentally, but let me emphasize that these are zero magnetic fields. Huh? So this is completely irrelevant, at least at this point. So magnetic brightening, as far as I know, takes place because of the fact that, say, in gallium arsenide, in modest magnetic fields, you can actually reduce the size of the exciton to beyond the normal Bohr radius, and it eventually becomes the magnetic length, and in this way the excitons become more bright. So in this case, this will require outrageous fields that we certainly don't have access to. I don't know if that helped. So there is a reference there, but maybe I'll take it.
Emre, I've invited you to unmute yourself. Yes, so now you can.
Sure, thank you. So thanks a lot for the detailed explanation. I thought these measurements were done at high magnetic fields at 14 Tesla. And I shared the reference. This is the work done by Tony Hines. They were applying a magnetic field to see the dark excitons, and they see a new resonance appearing. I was just curious if the features that you're seeing could be due to dark excitons becoming optically accessible.
I see. So look, I honestly don't remember this experiment. I can take a look at it, but I suspect that it's a photoluminescence measurement at a tungsten diselenide material. So again, I see absolutely no mechanism why in absorption this would, or reflection measurements that would make a difference. But as I said, these are 0 Tesla measurements. I mean, that's one of the appealing aspects of our measurements, that these, we have the evidence at 0 Tesla. I will also show you the finite magnetic field results too. Okay, so the measurement I showed, which is on the reproduced on the left-hand side, was taken at a base temperature of 80 millikelvin. So we wanted to study the temperature dependence. We went to 4 Kelvin, and then the resonance is still there, but it's broader. And we increased the temperature further. And if my cursor works, yes. What we saw is that at around 11 Kelvin, the resonance completely disappears, and beyond that, we don't see anything. Okay, so even though the actual exciton line hardly gets modified in terms of energy shift and line broadening, the Umklapp resonance disappears. And this is what we would expect, that it's kind of consistent with the Lindemann criterion within a factor of 2. And so it looks like there is a transition from a Wigner crystal at low temperatures or state with Wigner crystallites to a Fermi liquid, although we really cannot say much about what's happening in between, which is the most interesting problem in this case. Okay, so finite magnetic fields, in this case 6 Tesla. So you see that Umklapp peaks, particularly in one polarization, become substantially stronger. And what is happening here is that due to the Valley-Zeeman effect, the K-0 exciton resonances split. But if you look at the energy of the Umklapp resonances, they hardly show any splitting. And this initially was surprising to us, but then by invoking the nature of these Umklapp resonances as arising from the transverse polarized excitons, we had an explanation. Basically, the Umklapp resonances, whether they are sigma plus or sigma minus, they arise from large momentum excitons, which are polarized in plane. So in that sense, they're insensitive to the Zeeman effect, and therefore their energy hardly gets modified. And what that results is that one polarization in the sigma minus, the K-0, is closer in energy to the Umklapp peak, and that's why its strength is larger than the other one. Now, that gave us the idea that maybe we can make the Umklapp peak even stronger by tuning the energy of the sigma minus peak to higher energies using magnetic field and bring these into resonance. Okay, so indeed that the Umklapp energies are about 2 milli-electron volts, and the Valley-Zeeman effect with the G factor of 4.3 means that we can easily get our exciton into resonance situation. And this is really worked nicely. So you can see here that even without differentiation, we now see the signature of the Umklapp resonance crossing into the main exciton peak, the sigma minus polarized peak. And if you differentiate it, then you can discern the Umklapp peak much better. And I should really switch to the normal pen option. No, pen is not good. Sorry about this, because this really is very slow. Okay, I'll just stick to this one. So, this is nice, because now that we have an actual Umklapp resonance that we can see and identify its center frequency and line width precisely, what we did is we tried to look at the effect of disorder and extract its magnitude from the line width of the Umklapp peak. And from this, we were able to determine a reasonable estimate of the correlation length, which we believe is larger than the 5 lattice constant. So it looks like if you are to be precise, all we can say is that we have Wigner crystallites, which are maybe have about 50 electrons or so, maybe more, but we cannot say based on the spectroscopic signatures we have. And the main limitation is the strength of the umklapp resonance, as you have seen so far. So, so that brings me to the last point. So maybe I stop here, and since I see that there are questions. The first question is, just a moment, related to Emre's question, the large momentum excitons were forbidden from recombining because of translation symmetry, which is now broken with umklapp scattering. Might there be other selection rules that prevent the backfolded excitons from recombining total orbital angular momentum? Absolutely, excellent question. So this is precisely the reason why only 2 of the 6 umklapp resonances that I've shown you are allowed to sort of hybridize with the k equals 0, the fundamental exciton peaks, and acquire an oscillator strength. So basically, angular momentum, in this case, the perpendicular angular momentum is so mode 3. So we basically have, sorry, mode 6 in this case, because it's C6 symmetry. So we basically the states that can hybridize are those with L sub z equals +1 and -1, and the others would remain dark because of the fact that their angular momentum doesn't allow them to hybridize. Okay, so let me see the other. So the other question is whether we had the chance to look at temperature-dependent transport, and the answer is unfortunately no. So basically, two-dimensional semiconductors, they're very difficult to contact. So there is this large Schottky barrier, which basically, I mean, I'm no transport person, but which my understanding is that unless you really go to high electron densities, it becomes very difficult to do transport. So if you look at literature, you'll see nice transport measurements with 10 to the 13 electrons, or at maybe several times 10 to the 12. But at the densities where we see the Wigner crystal, it's essentially impossible to do a transport measurement, as far as I know, and we certainly haven't done it. All right. So okay.
Just a moment. I also see another question.
Yes.
Leonid, please unmute yourself.
Leonid, please.
Hi. Good to see you. Yes, so I just wanted to understand this correlation. So you're saying that you can estimate the correlation radius like 6 units.
Right. Yes.
So, but it's a crystal, so there are some directions, right? So I just wonder. I mean, you don't know the directions, and most probably it's like a polycrystal. So how you figure out that it's 5 rather than, I don't know, 100 or 2?
Yeah. So basically, I don't actually remember the detail about the direction or how we took it into account. But the main point is this, Leonid, that our starting point is the line width, right? So because the umklapp resonance has this fraction of the oscillator strength of the main exciton, so the radiative broadening is negligible. And indeed its line width is a factor of 3 or so smaller than the main exciton. So we basically try to describe, try to reproduce using this order the line broadening and the line shape that we get. And you see here we have different correlation lengths for the disorder, and then we sort of modify this correlation length and see how the fit gets better. So it really is like a first try. So I wouldn't put too much sort of emphasis on it, but you can see that if the correlation length were 3, lattice sites, then we completely miss this peak because of the broadening. But this is the level at which we.
And the position at least scales correctly with the magnetic field, or with the density, with the density of the electrons. The position must.
We only did at 14 Tesla. So so in that sense, I cannot talk about scaling of the size with the magnetic field, if that's what you mean, because this, I mean, as I tried to explain, that normally the resonance, when it's far off from the main exciton, it's very hard to put with good accuracy the line shape.
Right.
So basically at 14 Tesla, we have, or beyond 12 Tesla, we can get to this resonance situation. And then we have limited magnetic field value. So honestly, we only did it for 14 Tesla. And the maximum field we can have is 16.
Okay, thanks. Thank you.
So I also see a question in chat. If it's possible to observe a zero temperature transition from Wigner crystal to a Fermi liquid, or base temperature, I guess.
Yeah. So I think that the answer hopefully is tentatively yes. And I mean, let me put it this way. So I think what I've shown you is basically a rough first take on this, right? So basically, the experiment that I showed a while ago, sorry, I don't know why this is not working. So this transition was at zero magnetic field. So the reason I'm sort of rather tentative is that you know, can we say something about this transition, where exactly it happens, or what is there in this transition region? So with this kind of accuracy, with this kind of Umklapp strength, we cannot say much more. So that's why I would say one can, in principle, study this, but we would either need a much better sample where we also suppress possibly the radiative broadening, but most importantly, disorder broadening. And then we could get cleaner Umklapp signatures. Or we can do what I'm going to try to describe to you now, which is to enhance the interaction using FH1 resonance. So that's that. Is it possible to think about this crystallization in a trion framework as well? So in principle, one can think about, if you are looking at the attractive polaron, then the answer is yes. So in the case of attractive polaron, you can argue that that basically when you excite the system, you generate a periodic array of trions. Now, the point is this, that as far as we can see, our crystal is not spin polarized, or at least we cannot see its spin polarization. It might be affected by the fact that we do have an optical excitation. And, you know, the effect of lack of spin polarization on the repulsive polaron. So the short answer is no, because I'm looking at the exciton branch or the repulsive polaron branch. So this is basically the modification of the exciton, the free exciton, due to its interaction with the lattice. So basically, you can also ask this question: if I directly excite at the attractive polaron branch, what I'm exciting what I'm doing is a collective excitation of many trions. And in that case, I should also be able to see the periodicity, but this will only happen if my electrons are spin polarized. And in principle, at high magnetic fields, we should be able to see this. I must say that we haven't looked at features at the attractive polaron. But in principle, yes, there is a regime, but it's not relevant for the experiments that we're discussing here. Okay, so let me briefly, since I don't want to leave with the negative note that Umklapp resonances are weak, so they tell us, but what we can learn from them at this point with the sample quality that we have is relatively limited. So can we go around this limitation? And that's the answer is yes. And what we did is that we got inspiration from cold atom physics, where the interaction strength between two particles, between two atoms in their case, is controlled by the so-called Feshbach resonances. So the idea for the condensed matter community is that if the scattering channel that you're interested in, which we will call the open channel, in addition to it, if there is a closed channel, say distinguished by the different total spin of the particles, and if this closed channel supports a molecular state, and if this molecular state energy can be tuned with respect to the open channel, so there are many ifs here, but this works beautifully well. If you bring this molecular state into resonance with the zero energy open channel state, then you can dramatically enhance the scattering phase shifts and go to the so-called unitarity limit. Okay, so I want to show you that, even if briefly, that we can do this in two-dimensional materials. We cannot really use spins, but we can use layer pseudospins. Instead of magnetic fields, we'll use electric fields to tune the different channels, and then the mixing of the two open and closed channels with different spin in atoms is typically due to hyperfine interaction, and in our case, this will be coherent also. Wasn't fair. Let me end with essentially an epilogue. So this is actually going back to the first long-range colloquium I have heard from Liang Fu, which I found very motivating. He was talking about these trimer states in a bilayer system where A lattice consists of a Mott state of electrons, and B lattice has low density delocalized electrons. And so they have analyzed this as a potential system for superconductivity with repulsive interactions. So I'm not going to say much, but I just want to say that one can describe their predictions in terms of the language of Feshbach resonances, where the open channel consists of two electrons in the B lattice, delocalized electrons in B lattice. Closed channel is when we have an electron and a so-called a polaron, that is an electron plus an electron excited from A lattice to the B lattice. Okay, so this is, again, it's not occupied, but it supports a bound state, which is the trimer. And the presence of this trimer state actually results in a Feshbach molecule and leads to binding of the two electrons in the B lattice. Okay, so I think that I just wanted to convey that, I mean, partly because of this historical reasons and partly that the ideas of Feshbach resonances need not be restricted to exciton electron scattering, but can really allow us to visualize processes in bilayers in different contexts. So I'll stop here and thank you for your attention.
Thanks a lot. Please raise hands if you please use the raise hand feature if you have any questions. And I already see a question from Benjamin. Please.
Yes.
Okay, I'll.
Thank you for a lovely talk. I was wondering if you're looking into increasing electron exciton interactions in a bilayer structure, why not focus then on interlayer excitons that are then naturally dipolar and you don't have to rely on their polarizability? Is that just an issue of oscillator strength that's too weak of those?
Yeah, absolutely. I think that of course, interlayer excitons, as you say, interact more strongly, and actually we can also realize Feshbach resonances between interlayer excitons and electrons in either one of the layers. The issue there is that as you pointed out, its interlayer exciton oscillator strength is very weak. And so much so that there is in standard scenarios, you cannot really see them in optical absorption. So they become prominent in photoluminescence measurements. But we like the resonant measurements because this is much cleaner in terms of looking for these weak signatures like we have been. That said, so the structure that I've shown you, actually, we have, so I don't have the results here, but we, by tuning the electric field, but keeping the layers undoped at least, we can actually generate hybridized excitons that are superposition of intralayer and interlayer excitons. And so these guys actually do have a finite dipole moment, and therefore they would interact more strongly, but they also have the oscillator strength because of their intralayer component. Now, the issue is that at least in this sample, we could only see these in the absence of free carriers. So I don't think this is a fundamental limitation, but at least at this point, I mean, with the samples that we had, we didn't have this best of both worlds, that is dipolar excitons with a large oscillator, sizable oscillator strength, and itinerant carriers at the same time.
I see. Thank you. And if I can chance one more question, I don't know if this device is headed towards the same Wigner crystal realization, but it seems like the period of the Wigner crystal becomes comparable to this Moray period in this particular device. And I wonder if you've explored how those two length scales start to play with each other.
Yeah, so I think that of course, so the results that I've shown you were on a monolayer, and it doesn't make sense, in my opinion, to look for Wigner crystals in bilayer structures, particularly in structures like this with a small separation with the finite Moiré potential, because the best we can do here is Mott-Wigner states or generalized Wigner states, as my colleagues Feng Wang and Jishan and Qinfei Mak refer to them, in the sense that, you know, what we can hope to see here is breaking of discrete translation symmetry, that we can see order at 1/3 filling and so on. And these actually have been seen beautifully in Cornell and Berkeley experiments. But a true Wigner crystal, if such a thing exists, of course, in the light of disorder, this will not be the right place to look for it. And yeah, so but in our experiments, partly because of the large Moiré period of 24 nanometers, we only saw the Mott state. So the other experiments that I told you about had a period of 8 nanometers, and then they could see these fractional filling incompressible states. They did not look at umklapp resonances, but I'm sure that these will show prominently if they were to look for them.
I see. Thank you.
Perhaps since you mentioned disorder, I was actually wondering what role it plays in the experiment, and in particular, would it be possible to discriminate the situation when the electrons are all pinned individually in the local minima of disorder potential versus collective pinning of a Wigner crystal?
Yeah, I think that if the electrons were individually pinned in some random potential, we will not have an umklapp resonance, right? So whereas the collective pinning would result in umklapp resonance, even if, again, the size of the crystallite is not so large as we think is the case in our system. So, but of course, we're looking at several crystallites. I mean, our focus is still 500 nanometers. So most likely we have several of these crystallites with different sizes and whatnot. And that, I believe, is responsible for the broadening of the resonance. So, so I'm not sure I understand the question fully, but basically I would say that umklapp is telling us that we have a collective pinning rather than individual pinning.
I see. Thanks. I see no further raised hands. So thanks again for the very interesting talk, and see you everyone.
Thank you. Bye.